Do not forget, you can support the channel with a like, and you can also subscribe to be aware of the latest published videos. Thank you. We hope that here you can find the latest news, ideas, and discoveries from the scientific world.
New research shows that something strange is going on in the Butterfly Nebula. Planetary nebulae are formed when red giant stars reach the end of their helium fuel supply and eject their outer layers, becoming hot and dense white dwarf stars about the size of Earth. The shed material, enriched with carbon, creates stunning patterns as it is slowly blown into the interstellar medium. Most planetary nebulae have a circular shape, but some have an hourglass or wing-like appearance, such as the well-known Butterfly Nebula. These shapes are believed to result from the gravitational pull of a second star orbiting the parent star of the nebula, causing the material to expand into two lobes or wings. Like an expanding balloon, the wings grow over time without changing their original shape. Yet new research shows that something is amiss in the Butterfly Nebula. When a team led by astronomers at the University of Washington compared two exposures of the Butterfly Nebula taken by the Hubble Space Telescope in 2009 and 2020, they saw dramatic changes in the material within the wings. As they will report on Jan. 12 at the 241st meeting of the American Astronomical Society in Seattle, powerful winds are driving complex alterations of material within the nebula's wings. They want to understand how such activity is possible from what should be a sputtering, largely moribund star with no remaining fuel. The Butterfly Nebula is extreme for the mass, speed, and complexity of its ejections from its central star, whose temperature is more than 200 times hotter than the Sun yet is just slightly larger than the Earth, said team leader Bruce Ballack, a UW professor emeritus of astronomy. I've been comparing Hubble images for years and I've never seen anything quite like it. The team compared high-quality Hubble images taken 11 years apart to chart the speeds and growth patterns of features within the nebula's wings. The bulk of the analysis was performed by Lars Borchert, a graduate student at Aarhus University in Denmark who participated in this study as a UW undergraduate student. Borchert discovered roughly half a dozen jets, beginning about 2,300 years ago and ending 900 years ago, pushing material out in a series of asymmetrical outflows. Material in the outer portions of the nebula is moving rapidly, at about 500 miles per second, while material closer to the hidden central star is expanding much more slowly, at about a tenth of that speed. Paths of the jets cross one another, forming messy structures and growth patterns within the wings. The nebula's multipolar and swiftly changing interior structure is not easy to explain using existing models of how planetary nebulae form and evolve, according to Ballack. The star at the center of the nebula, which is hidden by dust and debris, could have merged with a companion star or drew off material from a nearby star, creating complex magnetic fields and generating the jets. At this point, these are all just hypotheses, said Ballack. What this shows us is that we don't fully understand the full range of shaping processes that work when planetary nebulae form. The next step is to image the nebular center using the James Webb Space Telescope, since infrared light from the star can penetrate through the dust. Stars like our Sun will swell into a red giant and form planetary nebulae someday, expelling carbon and other relatively heavy elements into the interstellar medium to form star systems and planets in the far future. This new research, and other time-lapse analyses of planetary nebulae, can help illustrate not just how the materials for the star systems of tomorrow will take shape, but also how the building blocks of our own oasis were produced and gathered billions of years ago. It's a creation story that is happening over and over again in our universe, said Ballack. The shaping processes provide key insight into the history and impacts of the stellar activity.